I started the recording a little bit late, but we'll have to live with it. It's the 5th of February, 2018, not the 8th. Okay. So we know that mass, we've got theta listed. I'm going to list mass, 69.0 kg. We want acceleration. And we know that what is equal to acceleration? It's not a trick question. F net, right? Not just the force, but the net force. So net force equals mass times acceleration. In this case, are we told that the sled is levitating up into the air or sinking down into the surface? No. So we know that the sum of forces on the y-axis equals 0. Okay. I'm going to shrink this a little bit. A lot. Okay, so sum of forces on the y is equal to 0. What, just for grins and giggles, what forces are on the y-axis? Give me one.
Gravity.
Which gravity? All of it? FGY. So, and I'm going to do forces up minus forces down. So the only force down that we've identified is FGY. What's the force up? I heard you say it, Wyatt. The normal force, yes. Okay. If those are equal to 0, what does that tell us? That normal force is equal to FGY. Normal force is equal to FG, cosine theta. Okay, we don't need that in this problem. We're going to need that in every single problem once we start doing friction. We're going to need that other axis to get our normal force, because normal force is not always as simple as you think it is. Okay, but knowing that we don't need that here, I'm going to set that aside. So we know our net force is going to exist on which axis? X. Yeah, it's the only axis left. We only work on 2 axes, thank goodness, because otherwise, well, it would just be a lot harder. Sum of forces on the x equals what? Oh, did I forget a force here? I did. I have an applied force. Force applied. Okay. Okay. So what are my forces on the x-axis? Give me one. I just put one in. Yeah, and we can say it's all the forces right minus all the forces left, or however you want to designate it. So the applied force is that upslope force. What's the force that's pulling down slope? FGX. Yeah, we have gravity on the x-axis because we're on a slope. Now, is this equal to 0? Net force equals ma. This is our net force, so I'm going to get rid of that and call this what it is. So this whole thing is actually equal to ma, because we know that, so we can just set those equal. I'm now going to get rid of that. So this is where everything else is going to flow from. I'm going to shrink this. So force applied minus, well, we know we have an expression for f of gx. Fg sine theta equals ma. Can we take this down any further? Is there anything else this is equal to? Fg equals what? Mg. So that's mg sine theta. Applied force minus mg sine theta equals ma. What are we attempting to solve for here? acceleration. It's all algebra, folks. Keep it algebra, don't make it math till the last. Because you want to have an expression that you can represent the situation with that doesn't involve any numbers. So you want to be able to build that expression. So force applied minus mass gravity sine theta divided by mass equals acceleration. On the test, getting to that equation is worth a point. You have to be able to create those expressions. We're going to end up doing major substitutions when we start talking about friction, and you need to be good at building expressions. I'll pause this for a moment. Finish this up. So how many sig figs do we get? 3? 2? 2? Yep. Okay. So this would be 21 meters per second squared for acceleration, which, like I said, that's crazy. I need to rewrite the problem, but you know, we'll take it. Okay, now we've got the box of Christmas cookies that we've hung up. It's suspended from by two cables, and we're pulling it upward, so it's got an acceleration of 1.5 meters per second squared. What's the force of tension on each cable? So we're going to break this down. We have a force of gravity on this object, which is equal to mg, and that's all on one axis. We don't have to resolve anything, which is always nice. We have this force of tension, which we can break into a force of tension on the y and a force of tension on the x. And I'm going to go ahead and label them as such. This is a 35-degree angle. I think in the glance through that I did, I saw a few people who made it a 35 with the wall, and that's just a matter of reading the problem carefully. You know, ceiling and wall are both used in force of tension problems. Whoops. Okay, so here we have force of tension on the x. Here we have force of tension on the y. And if we create an expression for that, force of tension on the y is equal to force of tension times sine theta. Force of tension on the x is equal to force of tension cosine theta. So I've got those listed, which is useful. Okay, so we know that there's an upward acceleration. Let me ask this. Is there any lateral motion? Is this thing moving left to right? Nope. So sum of forces on the x equals 0 equals force of tension x1 minus force of tension x2, force of tension cosine theta equals force of tension cosine theta. Okay, so that proves that they're equal, which we kind of knew, but that's like our geometric proof. All right, so our net sum of forces on the y is going to be equal to our net force. That's where we have unbalanced net force. And that's equal to mass acceleration, and it's also equal to all the forces up minus all the forces down. So what forces up do we have? Force of tension 1 on the y and force of tension 2 on the y. We only have one force down, which is, yep, Fg. And we know that Fg equals mg, so we're going to start writing in our expressions. First, though, I'm going to say this. Ma, I'm going to set these equal. Equals Ft1 sine theta, because that's my Fty, plus Ft2 sine theta minus mg. So now I've got an expression that gives me all of the variables that I have. I've got gravity, I've got mass, I have acceleration, I'm looking for force of tension, I have theta, so this is all using variables that I've got. Okay, so I'm going to move this up. And I'm solving for ft. One thing I know is that those ft's are equal, so ma equals 2 ft sine theta minus mg. This is where I very commonly see a kind of a weird algebra mistake, and people they forget the order of operations. So ma plus mg equals 2 ft sine theta. I can, and it's sometimes useful, I can do that and factor out an m. Whoops. Let me shrink some stuff here. Divided by 2 sine theta gives me force of tension. So go ahead and get some numbers in there. So this is one of those real pain in the butt, just sort of net force problems. You're sitting in your car on ice, and your friends apparently who have cleats on start pushing you around. Whoops. So we have Corey. Force of Corey is 3,268 newtons. And that's due north, which is nice because it lines up on an axis. Jacob does not have the courtesy to push straight along an axis, so we have to resolve his force. And it is north of east 25. I'm going to use a different color. So force of Jacob, that's a 25-degree angle. And we get 1,560. You must have eaten your Wheaties, Corey. Okay, so obviously Jacob's force can be resolved into an x and y component because it's not on an axis. We've got Isaac, also not courteous enough to push directly along a cardinal axis, so we have to resolve his force. And he is west of south at 15, so it's going to be like that. And these are not well drawn to scale, obviously, so this is force of Isaac. 2,941 newtons, and that's 15 degrees. And then Damien is pushing due west at 3,214. Okay. Force of Damien, 3,214 due west. This is bookkeeping. So you just have to find net force, and it's resolving. So you're going to do the thing we always do. Sum of forces on the x, sum of forces on the y, sum of forces on the x. We have all the forces west minus all the forces east. And what forces do we have to the west? Well, we have force of Damien. Is there anything else to the west? Yes. Plus the force of Isaac on the x. What forces do we have to the east? So I'm going to do that. We have just the force of, is that Jacob? On the x. Okay. So this is simple trig stuff, and I think most people got the net force right. Once you have net force, you're plugging it back into F equals ma. Here's where a lot of people slipped. You found acceleration, but you have to find a heading, because this is not directly on an axis. So you have to say, you know, degrees north of west, south of east, whatever it may be. These are not hard, and I think most people got the force right, and most people got the acceleration right, but most people missed the heading. So I'm going to go ahead and leave that as it is for you to, if you think you had an error, go ahead and fix it on your own. I'll let you rework problems. Okay, here. Sorry, I forgot to hit record again. equals Fg, which we can put back in for mg. So Ft minus mg equals ma. Because in order to get Peter Pan to fly, first you got to overcome gravity. And if you're just holding her there, obviously that there's still a force of tension in the cable. So force of tension in the cable is then equal to ma plus mg. We can factor out the mass. It makes for easier calculation. It's not essential here. It will be soon enough. So force of tension equals m times a plus g. And I'll let you get the numbers yourself. So putting in the 760 newtons, that would be the force of tension on the cable. Now, you could do a problem where you do something like compare this to the force of tension in the cable if Peter Pan is stationary. What would that be? 57 times 9.81. If Peter Pan's stationary, the force of tension is only going to be 559 newtons, 560 newtons. So interesting to think then about, problems like the one that you've got in the 5B packet where they're asking, well, you have this wire that can just support this much. What's the maximum acceleration that you can achieve? And the cable systems in a theater would be the same thing. You'd have to look at the mass of the actor and the rigging and everything and look at what the maximum acceleration that was allowable was before the whole thing snapped and sent Peter Pan tumbling to her death, which we don't want to have happen. Terrible thing. Okay, questions, comments, concerns? So this is kind of a preview of something we're about to see. You have a box and it's being pulled, or an object is being pulled by something. And we want to know what its acceleration is. So F net equals ma. Well, fantastic. We know that gravity is straight down. We know that normal force is straight up. We know that the applied force is being broken, Gesundheit, into two components. So if this is the applied force. We've got F applied sine theta, F applied cosine theta. That's pretty easy. Everybody gets that. What if I ask you to solve for the normal force here? So F of g equals mg. Is normal force equal to mg here? No. Here's why. So if we do a sum of forces on the y-axis, it's not rising into the air, it's not sinking through the ground, or we would be told, we assume. So sum of forces on the y, the net force on the y, is equal to 0. Well, that's all the forces up minus all the forces down. What forces up do you have? Normal force and applied force on the y. So you have F normal plus force applied y minus force of gravity. So normal force plus F applied sine theta minus mg. If we solve for normal force, is normal force going to be more or less than gravity without going any further? Normal force equals equals 0. So normal force equals mg minus F applied sine theta. In essence, you're helping the floor out because you're applying an upward force on that object. The floor has to do less, has to push less hard on it in order to overcome gravity. Now, has anybody here ever pushed a box? Has anybody ever pushed a box across the floor? Okay, plenty of times, plenty of times. You ever do this number? Where you're pushing down on it as you push it forward? Have you done that? Okay. Let's look at that situation. So I have Well, I'll tell you what, I'm not even going to do that now. We'll talk about that a little bit more tomorrow. But just, I want you to realize that normal force is not always going to be equal to gravity. It's generally in opposition to gravity, but it's not always equal to gravity, so be careful with that. Okay, keep working on 4B, and we'll hit stuff as we need to.